So I have an emitter, a common emitter amplifier circuit. I've got a source voltage, beta, R1, R2, R collector, and R emitter resistors. I have an input 5 kilohertz time varying AC signal, and it has a voltage amplitude of 2 volts peak to peak, which means 1 volt for its amplitude. And the first thing I'm going to do is just enter the values into Matlab just to make it easier for me to do the calculations. So I'm going to have R1 is equal to 5900, R2 is equal to 51,000, RC is equal to 39,000, RE is equal to 3,300, VS is equal to 12, and beta is equal to 90. Okay, I think we've got all the parts that we need. All right, so we'll go back here. And what we're doing then is we're gonna start. We know we have a PNP transistor. Really, when we have a resistor network like we have here, so we have this resistor network, then we are going to be able to calculate the voltage at the base right here. So we're looking to calculate the voltage there, and we can use our voltage divider equation, V of the signal times the resistor value for R2 divided by the combination of the resistors, and that'll give us our base. So we're going to call this, we're going to label it. So we've got the base here, we have the emitter here, and we have the collector here. We know it's a PNP, right? And so we've got, we've labeled it, we have the kind, the output on here. So whenever we have a transistor like this, the output is always, for an amplifier, is always on the collector. So this is going to be our V out right there. We'll create the graph in a minute. I think it's easier sometimes to go through and calculate all our voltages and currents first, and then we'll do the graph. So we're going to move on to E. Okay, so we're going to also insert a table. So insert a table. All right, so I've got our table is here. I'll move that down here where we can see it. To the bottom, I guess. Here we go. So VB, VE, VC, VCE, VEC, IB, nope, IE, IB, and IC. I always like to write them in the order that I know I'm gonna actually calculate them. So like I said, the first thing we're gonna do is we're gonna calculate the voltage at the base. So I'm gonna do that in Matlab. So I know that the equation is, let's see, I'll write that equation down here. My equation is, draw, let's go black. Go. So my VB is equal to VS times R2 over R1 plus R2. I'll go into Matlab. I'm just going to type that exact thing in. So VB equal to VS times R2 divided by R1 plus R2. And I get 10.8. So I'm going to plug that into my table down here. So 10.8 volts. Great. For my currents, I'm going to use milliamps for my currents. So these are all going to be in milliamps. All my voltages will be in volts. Okay, so great. We've got our VB. So we can check off our VB, and we're going to do VE next. So VE, we're going to, we've calculated here the VB here, and now we need to add 0.6 volts to get up to our emitter voltage. So we're saying that VE changes back to black. So VE is equal to VB plus 0.6, And so I know that that's going to be 11.4. Right, so I'm just going to do this also in Matlab just because, so we'll have all of our values we needed to calculate IE. So VB plus 0.6, 11.4. Right, so the next thing I want to do is I want to calculate my voltage drop across E. So I want to calculate my voltage drop across here, and I'm going to call that V sub RE. So that's going to be my voltage drop. And the way I can find that is just take my supply voltage right here and subtract VE. So VE here I know is 11.4 volts. That's going to be my VE. So to calculate VRE, I just need to do VS minus VRE, or VE, sorry. VE. And that'll give me the voltage drop. And then from there, I can find the current. So the current in through ERE then is just IE is equal to V of RE divided by the resistor, just using Ohm's law there. Okay, so let's do that. So V of RE is equal to V of S minus VE. And that gives me 0.644, so that's the voltage drop, which makes sense because I've got 12 volts at VS and I've got 11.4, so that makes 11.4 at E. That makes sense. So now I'm going to do IE is equal to V of RE divided by RE. And I get 0.195 milliamps. So I know my V, let's see, did I have, yeah, okay. So right here, I'm going to write 0.195. Great. And now I can calculate next my IB. So IB is going to be, so I've got my IE now, so I've calculated that. So my IB is equal to IE over 1 plus beta. And remember that where that comes from, right? IE is equal to IB plus IC. That's from Kirchhoff's current law, right? So what I have here is I have my current flowing from E this way, and it's got some of it splits and goes to B, and some of it splits and goes to C. So I've got all of my current for B and C in E, and then it splits off. And so that's where this comes from. That current has to add up. So, and I also know here that my IC is equal to beta IB, and I'm going to plug this in up here. So I get IE is equal to IB plus beta IB. And so IE is equal to IB times 1 plus beta. And then I just rewrite this equation to give me this equation right here. So I'm going to plug that into Matlab. So my IB is equal to IE divided by 1 plus beta. And I get 2.14 times 10 to the minus 6. So plugging that into my table, I get, actually I'm going to write it, 0.002. 0.0021. There we go. All right, and now I can calculate IC. So I can go back to my IC equation, this one right here, and I can calculate my IC. So my IC in Matlab is just IC is equal to beta times IB. Now I get 1.9. So here I'm going to get 0.193. Great. Okay, so now I have IC. So if I go back to my picture again, I now can calculate let's see if I just erase a few things here. Clean this up a bit. Okay, so now if I want to if I know IC, I know VC, right? So so if I know my IC and I know my RC, I can calculate VC. So this is the VC I'm looking for, and that's just going to equal VC is equal to IC times RC. That's the voltage drop across this RC resistor, and I need that voltage, the drop across it. I need that voltage at the point VC in order to have it left to get to 0 beneath that resistor. So VC then is equal to IC times RC. I get 7.5. So 7.5 goes into my 7.5 volts right there. And now if I want to find VEC, I'm going to take 11.4, right, and subtract 7.5. So I'll just do that here. So VEC is equal to VE minus VC. I get 3.8. So plugging that in here, I get 3.8 volts. Okay, great. So I've completed my my numbers here. So let's make our graph. So we're going to have a graph. Looks like this. And I'm going to do the load line first. So remember on my graph, I have VEC and I have IC over here. This is going to be in milliamps and this is going to be in volts. Okay, so the first thing I need to do when I'm making my load line is I need to think about cutoff and saturation. Way back a long time ago when we were doing transistors as switches, we just knew how to turn a transistor on and off. And so those are the two cases that we put in our load line. So if I do cutoff, that gives me my maximum VEC. So I'm going to have, this is RE, this is E, this is C, and this is 0. So this is RC. And so if I were to measure the voltage at E, because there's no wire connecting E to C, I'm just going to get my V value here. So this is going to be my VE is going to equal 12 volts. And the reason that's true is because if there's no current that flows, there can be no voltage drop across RE. There's no voltage drop. So I haven't lost any voltage when I get to E, so it's still at 12 volts. The same is true at C. There's nowhere for current to flow, so I have no voltage drop across RC. So that means at C, my VC has to equal 0 because it's connected to the ground. So that means that my VEC has got to be 12 volts. That's the max value that I can have. And now for saturation, saturation gives me the maximum value for my collector current. So that's what we're going to put on the y-axis. So again, I've got RE, this is E, I've got C, I have RC, and then ground. So now all of a sudden with saturation, this is the max current that can flow through our transistor from the voltage source through E, through C, through the transistor, through C, and to ground. And so to calculate that, then I want to find that collector current, the current that's going to run through here. So I'm going to say that's IC is equal to V over, these two resistors are in series, so I can just add them. So I say RE plus RC. And so that's what I'm going to calculate in Matlab. And I'm going to call, instead of calling this IC, I'm going to call this IC sat. So ICS for saturation. So IC sat is equal to Vs divided by Re plus Rc. And I get, let's see, what do I have over here? So 0.28, just make sure that's right. So Vs, yeah. Okay, so I'm in milliamps. I'm going to be at 0.28 milliamps. So I'm going to draw that over here, 0.28 milliamps. And I'm going to draw the load line. But the first thing I want to do before I do that is use my values here, this value and this value, to show where we're operating on the load line. So 3.8 is about here, maybe a little less, but that's good enough. And then 0.194 is about, say, maybe here, 0.194. So if I go up like this, hopefully we can get these. This should be on the load line, so something like that. That's my operating spot, and then here's my IB is going to be, IB is 2.1 microamps. And so we've got that. And now what's next? We have, what is the voltage gain here? So my voltage gain, AV, is equal to a negative RC over RE. So we can calculate that. So I've got my AV equal to a negative RC divided by RE, and that's a negative 11.8. So if I think about an input, so notice I haven't even talked about my time varying signal yet. I needed to set this whole circuit up to understand the bias, to understand my output, right? And so what I need to do now is think about my time varying signal. Notice it's 150, where is it? 2 volt, oh, it's 1 volt. So I've got a 1 volt signal that looks like this. This is time, this is voltage, this is 1 volt. When I bias it, so this is my input signal. When I bias it on the base, then what I'm doing is I'm just taking this signal, the input signal, this one, and I'm just changing the 0. So notice the 0 is at 0 volts. It's centered around 0. When I look at my base voltage is 10.8. So all I'm doing is I'm just going to say I have a new 0 for my signal at 10.8. This is volts. And so I have the same signal. The amplitude is still 1. Right? So notice this distance right here is 1 volt. This distance right here, from here to here, is 1 volt. Right? And then, so this is going to be my biased input. And now looking at VE, looking at VC, VC is 7.5. So this is going to be my output. So the output is on C. So it's on the collector. So my output, looking at my circuit again, this is right here is where my output is going to come out. And so I'm going to have a signal like a wiggle. And actually the wiggle is negative. So we start and we flip. It's out of phase by 180 degrees. So my output is going to be at 7.5 volts, right? And it's going to look something like this, like that. Now the problem is, there's a problem with this circuit. And the problem is that if I think about a 1 volt signal, so if I have my amplitude for my input is 1 volt, and I want to find the output, so this is the input, my output should be, so V out, just time varying, right? Just the time varying should be V in times the gain, and so AV, and so that's going to be 1 volt times 11.8, and a negative 11.8. Right? So I should get something out that is a negative 11.8 for an amplitude. So if you think about that, right? If it was centered around 0, it would be like huge, and it would be like this, right? The frequency doesn't change, but the amplitude definitely does. So this would be 11.8 here, right? And 11.8 here. And the problem is we only have, so that should be our output. But what happens is if you look at this circuit, right, I can only operate between 0 and 12 volts. So I've already brought it up to 7.5 volts. So what's going to happen is if this is 12 volts, uh, so my output would be, let's see if we can draw this. So this is at 7.5. And if I add 11.8 to that, I'm going to get 19.3. So 19.3. And if I subtract 11.5 from that, I'm going to have -5. Let's just say -5, something like that. So I'm going to have an output that looks like this, right? But my circuit can only handle, say this is, let's make a kind of a range. So my circuit can only handle, say this is 12 volts and this is 0 volts. So I'm only going to get the signal that's inside of here. So I'm clipping my signal above and below. So my whole signal doesn't pass through. So what I would need to do is I would need to think about the maximum signal that I could actually input into my circuit. And so if I want to think about that, then if I say that I have, my signal can really operate, let me move this back to black, can operate, between 0 and 12 volts. So really what I need is centered at 7.5 volts, right? I need to go, let's see, to get to 12 volts, that's going to be 4.5. So the max I can have is 4.5 volt signal, right? So so then if I can only have a 4.5 volt signal, then, and my gain is 11.8, then I can say that my V out over my V in is equal to 11.8. So I want to find out what V in is that will give me that the V out that fits. So I can say, okay, my V in is equal to V out divided by 11.8, right? I've just rewritten this to get my V in alone, and that's going to equal 4.5 volts divided by 11.8. So let's calculate that. So let's say 4.5, let's just make sure, 12 minus 7.5, at 4.5. So 4.5 answer divided by 11.8, or let's just do it divided by AV, right? So the maximum V in can be is 0.38 volts, right? So if I don't want my output signal clipped, then the biggest signal I can have is a signal of 0.38 volts.